everybody. Welcome back to Fossil Friday Chats. I'm one of your hosts, Brittany Stoneberg, the Outreach and Communications Coordinator for the Western Science Center.
Oh, me. I'm Gabe Santos from the Alf Museum.
Yes. And welcome back. And today we have with us talking about a Silk Road paleo adventure is paleontologist Dr. Wynn McLaughlin. Hey, Wynn, it's really good to see you. Yay!
Howdy, everyone. Thanks so much for having me on as a guest. I mean, it's been a little funny realizing that I'm technically local, and yet here we all are teaching and lecturing from our living rooms, or, in my case, my lovely, comfy teaching chair.
Our new normal, right?
Yeah, our new normal for sure. I'm a professor at Pomona College, so technically I'm here in Southern California in Claremont for all of y'all tuning in. But talking about some of my research I did for my PhD and kind of ongoing work for the rest of my life in Kyrgyzstan. And so I kind of wanted to start with, first of all, I would also like to say, feel free to interrupt me. I'll try and watch the chat. And if I don't see the chat, they'll yell at me. And please interrupt me if you have questions, because I wanted to give a little bit of background on a really cool, unusual part of the world, the neat fossils coming out of there, but a little bit of my story of how I ended up working in a place I admit I couldn't find on the map before I started working there.
Awesome. Before we get started, Wynn, really quick, I just want to send a very special shout out to my co-host, Brittany Stoneberg, for the publication of her first lead authored paper on fossil horses. So, yay! Go, Brittany!
Thank you. And thank you a lot to my co-authors. It was definitely a group effort. Dr. Andrew McDonald, Dr. Alton Dooley, Eric Scott, and Charlotte Homan. We all been working on these, what Wynn and I have been affectionately calling doll ponies for about 3 years. So congratulations to my co-authors, and yay, did it.
Slightly bigger pony than I talk.
Yeah.
We'll drop the link to Brittany's paper in the chat in a little bit, but for now, let's switch it over to Wynn.
Yes. And just as always, like, again, if you guys have questions, Wynn may answer them during the course of their lecture, or we'll get to it at our Q&A session afterwards. So we'll try to get to as many as we can.
Okay, so as I mentioned, this is such a kind of remote part of the world. This is over in Central Asia, and just here's kind of an assortment of photos that I really like that encapsulate a little bit of what it's like working over there. This is, I'll admit, a little bit of the sort of all a Jurassic Park and Indiana Jones horribly combined into effectively what I call my field work. And I've been lucky enough that I've gotten to go 5 times, and I spent a year living in Kyrgyzstan, which is really when my research kind of took a lot of different directions and changes. So I'm a vertebrate paleontologist, but unlike many of the past guests, and to the disappointment of every small child that talks to me, I don't work on dinosaurs. I work on fossil mammals. And my interest in these fossil mammals in Kyrgyzstan kind of came back to this much bigger picture question that a lot of paleontologists are working on. Instead of studying a particular group of animals or some sort of kind of physical process, how hard do they bite, how old are these rocks, all of this different information, I'm really interested in what can these fossils tell us as tools about changing landscapes and changing climates and ecosystems in Central Asia in the past. Now, why Kyrgyzstan? Why not work somewhere a little closer to home or any of these other particular places? Paleontology is all over the world. It comes back to this relationship between the earth, the environment around us, and modern people living in these lands. So geology results in most of the hazards in Kyrgyzstan. This is an area with earthquakes and landslides and glacial outburst flooding, and a lot of these big potential natural disasters that have the possibility to damage lives, damage property, and our past environments give us a clue of how we got there. That said, though, while there's a little bit of a history of fossils being collected in Kyrgyzstan and some of the surrounding area in Central Asia, most of these fossil localities have never been published. They were found making maps looking for oil, a little skull and crossbones marked on the map and kind of moving on. And so I'm really interested in these fossils, not only for what they can tell us about these modern hazards, but also what they can tell us about how life and landscapes are intricately connected and changed through time. Specifically, Kyrgyzstan sits just north of India. So if we look at China on a map, it's on this northwest corner of China. It's a pretty small country. It's about the exact same geographic area as the state of Nebraska and fairly similar population. There's only about 6 million people living in Kyrgyzstan. But this has been a vitally important part of the world for millennia. So right here in the heart of Central Asia is this area where the famed Silk Road crossed. This connected what we sort of referred to as the East to the West, and the exchange of ideas and trade goods, but also of people. So our modern landscape, our modern cultural landscape is a reflection of this trade and human ideas that were exchanged through this area that really beautifully mirrors what happened in our geologic deep time as well. We have different areas with different animals evolving and going extinct and interacting with their environments in Europe and in Africa, in Asia, connecting into North America. And this Central Asian area acts as this sort of boundary to filter out what animals and plants were able to move between these different areas. And these animals moved to match the landscapes they were living in. So as our tectonic processes shaped and changed this landscape, some animals benefited and some had to either go extinct or move to new places. Now, this landscape itself is, oops, trying to get my slide. There we go. So here's kind of zooming in on Kyrgyzstan. This landscape itself today is dominated by these huge mountains. In fact, for fun trivia that can periodically come up, Kyrgyzstan has the highest average elevation of any country anywhere in the world. It's dominated by these mountains that run roughly east-west, called the Tien, Shan, or Heavenly Mountains. And these huge sets of mountains are there because of the same process that gives us earthquakes. India's its own separate continent. It's smashing into Asia. And just like if you have a pet dog at home and a lovely hallway rug, you throw a dog toy down that hallway and the dog hits the rug, crumpling it up in front of it. That's effectively what India is doing to Asia. And as Asia as a continent is crumpled and folded, periodically those folds get sort of brittle and break through on these huge earthquake faults. So our map of where we get large earthquakes and common earthquakes, our seismic hazard map for the world, often reflects these boundaries between different continents. And if we move in on Central Asia, this is an area where we're smashing India into Asia. So we're faulting and folding a lot of this area. We have really interesting things going on with the Mediterranean. And it's just sort of this bad Goldilocks perfect mix of all of these different plates coming together to result in the highest seismic hazard or highest probability of earthquakes and large earthquakes of anywhere in the world. So this highest average elevation Kyrgyzstan has is unfortunately coupled with the highest probability and hazard of earthquakes anywhere in the entire world. Now, this is kind of a cool story, but what does this really mean for people living there today? What does it mean for working there? And why is a paleontologist spending a bunch of time talking about earthquakes? Well, this was the, I think, absolutely stunning view from my apartment in Bishkek in the capital of Kyrgyzstan. We had these incredible mountains that get up to 18,000 feet, just barely behind the city, rising above the flat area of plains where the capital city is. This big change from this flat area to these huge mountains marking pretty much the rest of the country is because this is an earthquake fault. So here's a city with 1.5 million people living practically on top of an earthquake fault that has a history of 8.0 to 8.5 magnitude earthquakes. Really, really big earthquakes. Still kind of funny why a paleontologist is here, though. But we got to come back to this part where our types of different organisms tell us about what ancient landscapes were like. Today, if I went out to the top of the Cascade volcanoes in Oregon or Washington, and then I went down into the valley bottoms, I'm going to see different plants and different animals living in these different types of ecosystems. So we have animals that specialize for living in mountains. I can see that in the past as well. So I can look at these fossil mammals, primarily from Kyrgyzstan, and try and tease apart when they change from being animals that live in nice open lowlands, kind of forested areas, to animals living in the types of landscapes that we see from, these are all pictures from my fieldwork there in the last several years. These high alpine environments, lots of mountains, kind of high steppelands like we think of for much of Inner Mongolia. And putting in the timing of when these landscapes change lets me then estimate how big many of these past earthquakes were. If I can date the rocks, so how old is this layer compared to our surface today? How many times has that been split by earthquakes? How big were those earthquakes? This is all data that we need this age constraint on. Now, in most of the world, we would send a geologist and not a paleontologist to go do this and just date a lot of the rocks. But we don't have the right kind of rocks in Kyrgyzstan, so we're stuck with whatever our fossil animals running around on that landscape were. Now, in the case of Kyrgyzstan, my most common fossil is, somewhat surprisingly, a rhinoceros. This has kind of been a fun story in my own personal career for what I work on in paleontology, and that just as Brittany is now stuck on doll ponies, the cute little tiny horses, kind of accidentally, I work on rhinos quite a bit now because they're, again, just this most common animal. And these animals, these rhinos that were living in Kyrgyzstan, are a bit different than if we think about rhinos today. Instead of being a tank with kind of big horns on the front, these guys didn't have horns. They lack any sort of connection on that nose bone for where you could have stuck a big horn, but to make up for it, they had two big tusks that stick out of their lower jaw. So this was still not maybe the cuddliest of all animals. And it's proportioned a little oddly compared to our rhinos we have today. Our living rhinos are all fairly chunky critters. You know, our real unicorns have curves, but these fossil ones are maybe even taking that a little bit farther. Their legs are proportionately quite short, and their bodies are really, really round and barrel-shaped. So I'm trying to propose and spread the term corgi rhino as a great way to describe these. So I would appreciate if y'all would join me in adopting corgi rhino as the common name for these rhinos coming out of Kyrgyzstan. And this is a picture of excavating a leg. So unlike, again, Jurassic Park or some of our kind of images of what fieldwork is like, it's a lot of wandering around, staring at the ground, trying to find the one little place that a similar colored bone is sticking out of this dirt, and then very, very carefully trying to excavate around it. Now, when I say that my most common fossil is rhinos, this isn't just, oh, I found rhinos at a lot of different sites. Some of the places where I've found fossils are over 75%. Over 3/4 of all of the bones I find are rhino, with just a smattering of other animals. So whatever was going on in this ancient fossil ecosystem was quite different than these ecologies we see today. If you were to go to Africa on a safari, you might see 1 or 2 rhinos, likely far in the distance. These are rhinos that were probably living in big herds. This really common percentage we see of them tells us that there's something different than what we observe today. So I have at least 2 different flavors of rhinos and slightly different sizes. Every single one of the sites that I've found fossils in Kyrgyzstan has rhino bones. And they're often joined by things like horses, deer, gazelles, and occasionally some of our smaller things. I get a few little rat fossils. And for the reptile fans, this is about as close as I'm going to get. I have a lizard jaw and a fragment of a tortoise shell. Now, from a geologic paleontological perspective, these are relatively young sites. The fossils I'm collecting in Kyrgyzstan are between 5 and 9 million years old. So these are animals that are similar to what we see today. They pretty much all have modern relatives, but their modern relatives might be living in very different places than Kyrgyzstan today, which again is a bit of a clue about these changing environments. If I have rhinos and gazelles, and we'll get to things like giraffes and hyenas, this is an immediate clue that maybe this ancient environment wasn't high alpine meadows. This might have been more like a savanna where we would think about getting all of these animals in combination today. The catch is, though, one thing that's been a really big challenge of going and working in Kyrgyzstan, where there's not been a lot of previous research done, is there's some new animals. Now, when I first started being a paleontologist, when I first started studying this, I thought, wow, maybe someday I'll get to name a fossil animal. That would be so cool if that ever happens. It turns out it's actually a lot more common than I thought before I became a paleontologist. When we go to new places, or when we spend more time even going through collections that have been in museums for hundreds of years, we very frequently find new groups of animals or new species of animals. So as I collected more and more rhino bones, one of the things I found that will hopefully in the relatively not too distant future be on display at the Western Science Center is this mostly complete skull of a rhinoceros. The tip of the nose is over on the left-hand side. The one part missing is the kind of upper jaw, kind of front of it right here, little tiny eye holes, big back of the head to attach lots of muscles, and not a lot of space for brains makes up our lovely little corgi rhinos here. And I looked at this skull and I could tell it was a rhino, but the catch is it didn't look exactly like any of the other rhinos I knew about from the area. There were differences in kind of the shape of the skull and the back, differences in how long its nose was, how the teeth were shaped. Was the last molar shaped like a triangle or a rectangle, something that distinguishes many different rhinos? And I kept kind of comparing it to all of these known species and going, oh no, I think this might be new. Now, on one hand, that's really exciting. On the other hand, it's a little frustrating, and that it no longer tells me quite as much about how old the rocks are. If this is something that's brand new, I can't compare it to an area that has really good dates. So it has sort of a knowledge of how old these different layers are in comparison to the fossils. Thankfully, there's still other useful animals for this dating part, and I can concentrate in on what does this rhino tell me about where it fits in its family tree and what kind of environments it might have been living in. And today, again, we think of rhinos as not being a really common animal. They're running around in Africa, Southeast Asia, and India. But if we look at their fossil record, this used to be a much more diverse and really widespread group of animals. So rhinos are actually from North America. They are made in America, so to speak. Our oldest fossils, about 50 million years ago, are all found here in North America before they spread out to other continents. Now, even looking at this kind of smaller time slice of the past that I've concentrated on, and this map here is looking at 20 million to 5 million years ago, we still have a wide distribution of where we find rhinos in the world. And these rhinos kind of have different ecological niches or sort of roles within an ecosystem that they occupy, just like our rhinos we see today. We have rhinos that like to graze and eat grasses. And we have rhinos that pretty much just eat kind of softer, squishier leaves. They browse off of trees. So we see different rhinos today in different places, And we can look at a lot of these same characteristics in the shape of their nose and the shape of their teeth for how they were eating in the past. So the rhinos that I have in Kyrgyzstan fit in much more with these browsing rhinos, the rhinos eating trees, and not rhinos that would be real happy with these grasslands that we see in Kyrgyzstan today, these high alpine steppes. So one of my areas of research is kind of putting this together into a family tree and using this then as a tool to look at when these rhinos change these kind of ecologies as a sign of when these landscapes and environments were also changing. When did Central Asia go from a nice, happy savanna to high alpine mountains that unfortunately don't have rhinos running around in them today? Now, I have a bunch of different fossil sites that this material is coming out of. And while rhinos are the most common, they're far from the only fossils there. And these fossil sites are so full of fossils that often, once you figure out where these fossils are coming out of, you can literally sit down, dig a hole, and you will find multiple fossils in a hole right next to you. This is a really quite rare thing. Most of the time, fossils are not highly concentrated within a locality, a place we go to look for fossils. And for many of the other sites where I've worked, I spend hours and hours wandering around, staring at the ground, and I'm really excited if I find a single horse tooth. Yet, how do we concentrate fossils in a big pile? Why do I have all of these things that came from the same place? I have my rhino skull on the bottom here, kind of going counterclockwise from that. We have gazelle horn cores, so the bone on the inside of the horns for gazelles, a deer jaw, a hyena jaw, and a baby horse jaw, all of some of our fossils coming out of these sites. Well, we have to do something to collect the remains of all of these animals. Oops, I guess I'll explain that here. So what I hypothesize has happened is that something has caused a bunch of animals all to die at once. Now, we call these mass death assemblages, or a death assemblage where some sort of catastrophe put all of these animals together for paleontologists to come find later. But we'll have to think about what kind of clues we can piece together and how this relates to the story of changing landscapes. But let's sort of build in a few of these other animals to get a better look at this whole ecosystem. One of my next most common animals after these rhinos that I find in Kyrgyzstan are deer. We think of deer as being all over the place. They even come into cities quite frequently. We have them North America, South America, all of Eurasia. There's several deer that get into Africa. They're even unfortunately invasive in parts of Australia. So this is a very successful group of mammals that have taken over pretty much the entire planet. But deer are, evolutionarily speaking, a really recent invention. We don't have things that we could look at and be like, that's definitely a deer, until about 9 million years ago. So unlike the rhinos that are a little harder to piece together, they have a long history of rhinos all over the place, and how old is this rock from this rhino? Kind of hard to tell. These deer are really a cool tool that if we find a deer fossil anywhere in Kyrgyzstan, we can say these rocks are younger than 9 million years. And we can even look at some kind of characteristics in the antlers. Our first deer that evolved in Asia are really weird looking. It takes a while for deer to sort of figure out what makes an antler. Now, if we pause a moment and think about how strange antlers are, this is bone that grows out of an animal's skull over the course of a single year, and then they shed it at the end of the year and have to regrow all of that bone again. Imagine regrowing your arm. I mean, this is a lot of investment in terms of energy, and all for a weapon to fight other males or impress the ladies with for sort of access to mates. Now, these deer fossils coming out of Kyrgyzstan, I think, are also a neat parallel in that while we don't have rhinos running around Kyrgyzstan today, we do have deer. So this picture is a little hard to see on this right-hand side, but this is a petroglyph that's between 4,000 and 8,000 years old in Kyrgyzstan with a outline of a little deer. We can kind of see in this dark splotch, there's the lighter body and head and these branching antlers coming up. So this is an animal that people have been interacting with for thousands and thousands of years in this landscape. One of our animals that makes it through this changing landscape, changing climate, mountain building events to sort of give us some clues for what it takes to live in this environment and how animals here might be impacted by some of our future change. Horses are another animal that's still there today, hugely important for the culture, but we have this great fossil record of horses in the area as well. And they're also really useful for telling how old our rocks are. Our modern horses today all belong to the genus Equus. So we have zebras, we have domestic horses that are all part of this same branch within our horse family tree. But going back even just into our ice ages, we have other branches, the Hyperionine horses, that are also running around sharing these ecosystems with our Equus, our equine horses. They look really quite similar. They were a little bit smaller, and they still kind of had the little extra remnants of side toes. Horses started out small with a bunch of toes, and through their evolutionary history, they've gotten bigger and gone down to just having this one hoof of our modern horses for running in these wide open environments. And that's going to be our little clue for how and why horses are such important fossils to look at in this area. This transition horses make from living in forests, eating trees, needing to sort of dodge more than be able to run really fast in one direction, changes when we have these big open spaces like grasslands or alpine steppe lands. So the horses need to be able to eat the grass and run away really fast from some of the predators. So looking at what different horses move into the area is a really great way to tell when this environment shifted, when the ice ages started in this area, as well as when mountain building made these different ecosystems. I have at least 3 different individual species of horses in Kyrgyzstan, like this jaw. You're looking down on the chewing surface, and here's the sort of front of the jaw on the left-hand side. And here's an artist's reconstruction of what some of these horses would have looked like. Relatively similar to our horses of today. Now, our horses needed to run away because of some of the things that were potentially around to eat them. The main carnivore fossil, which carnivore fossils are pretty darn rare in these sites that I've found, are from hyenas. And I have 2 different flavors of hyenas. Now, today we think of hyenas as kind of scary animals. They get a little bit of a bad rap, but they're fascinating mammals. They're quite big, and they're really unique in that they can both hunt, so they can be active predators, but they're also really great scavengers. They can kind of eat anything, including bones. Now, our hyenas we have today are sort of wolf-sized, and I have one wolf-sized hyena. This is a pretty scary animal that would have been running around. But it's not the scariest. Our other hyena that could have been snacking on our young rhinos and definitely eating the horses is a grizzly bear-sized hyena. Now picture something, a hyena the size of a grizzly bear, but with long legs, so able to run really fast, and with that short, bone-crushing sort of musculature and jaw of our modern hyenas. If you ever get the chance to time travel and we develop a way to go back and see all of these cool fossil animals, I don't actually recommend time traveling back into our Miocene epoch in Kyrgyzstan, because that's maybe not an animal you want to meet. In addition to our hyenas, I also have a small saber-toothed cat. And this again mirrors a lot of what we see today. This petroglyph, this rock carving that this one's estimated to be about 2,000 to 3,000 years old, depicts ibex, so a type of kind of mountain goat, and then these kind of faint 3 petroglyphs in the top here are snow leopards. So large cats are still one of our our main predators in these ecosystems today. For fans of kind of bizarre fossil critters, we also did have giraffes running around Kyrgyzstan. And this is another one of the animals that really suggests we've had some fairly major changes in our environment. We don't see giraffes living in the Himalayan mountains today. They're pretty much limited to sort of lowland areas. So this is all really important, again, not only for studying these individual fossils. You're all here for Fossil Friday, so you're obviously fossil fans, but what this means for this really big picture of how do landscapes and ecosystems change? How do we go from this scene by Mauricio Antone that is set in the Mediterranean, but Kyrgyzstan would have been very similar environments and similar animals about 20 million years ago, with horses and rhinos, some of these predators, in these kind of semi-open areas with lots of forests. This would have been a lovely place to live. How do we change that to something a lot more like these Ice Age scenes? So this painting by Julie Seelan is a Ice Age scene from inner China, where we have things like woolly rhinos and some of these hyenas hunting groups of ibex again. What does it take to shift and change these different environments? And how quickly can we make this change? So this is where that geology and earthquake hazard part comes back into studying these groups of animals. To get to this ecosystem we have today, this high mountains of the Tien Shan, we have to really shift this local topography. We have to have these big earthquakes to crumple up all of this land and build these big mountains. But mountains, this topography itself, also changes climate. If we go back into our Miocene, if we go 15 million, 20 million years ago, our monsoons of India would have swept all the way into Central Asia and had this beautiful, wet, rainy season. This would have been great for having forests, for having all of these trees and these nice kind of wooded areas for a lot of our critters to scamper around in. But as we keep having big earthquakes and every time forcing up these mountains a little bit more, eventually this uplift of these mountains on these earthquake faults makes the Himalayas and Pamir Mountains high enough to block this monsoon from reaching into Central Asia, for reaching all the way into Kyrgyzstan. And suddenly, our nice rainy season disappears. We're left with probably increasingly long droughts. At first, it might have only been 1 year out of every 50 that this monsoon failed to reach Central Asia, causing droughts. But as time went by, maybe year and year after year, no rains would make it into Central Asia. And these ecological communities, these environments of plants and animals, face these mega droughts. So this is my hypothesis for why we see all of these different fossils of animals piled up together in these mass death assemblages, these bone beds. These reflect when we had droughts and the animals sort of most vulnerable to that. Ones that couldn't move away from the area, that couldn't follow where the water was. And on the really sad note for the paleontology, often our older animals and our younger animals. So many of my fossils are either from elderly individuals or babies. These are the animals that wouldn't have been able to make the journey to wherever there were still water sources and needed those resources kind of a little bit faster. They leave really cool fossils behind, but it always makes me a little sad when I think like, oh, this was a baby pony that didn't make it. So that's our kind of story of how we shift to this environment that we see today in these kind of modern pictures along the bottom. This high alpine area with primarily grasses and kind of shrubby bits and not these big open forests. So really changing our types of animals we see in these different places. And not only does this matter for our sort of earthquakes, the how old are the rocks is how many past earthquakes, how big those earthquakes are, and these possible hazards, but a lot of other reasons. So this top map here is a earthquake probability model. This is the probability of there being a earthquake of particular sizes and how big that earthquake would be in terms of how much shaking over kind of how broad of an area. Now, the options are not too bad to really quite bad. Hotter colors are more shaking, worse earthquakes. The difference between these two models that were made is the timing on when the mountains started being uplifted and built in this area. And where this is really scary with my research is a lot of the animal fossils I've found are younger animal species than had been previously sort of thought there should be for the ages of these rocks. I get a lot of these deer fossils that are 9 million years or younger. Now that's a problem because some of these sites they thought were 30 million years old. If we have this much scrunching together on earthquake faults in 30 million years versus that same amount in 9 million years, it means we had to have had bigger earthquakes more frequently to squish rocks that much in that short period of time. So unfortunately, a lot of the data we're producing with these fossils suggests that this really is a very high risk area. Now, this is important for making these maps of where is going to be the safest places to put dams and hospitals and schools and all of these new roads. This is not an insurmountable problem, but something that we really need this full data set to figure out what's going on. This isn't our only geologic hazard facing Central Asia and Kyrgyzstan. This is also an area that's being very heavily impacted by climate change. High elevation is very sort of temperature vulnerable areas. This bottom picture is just from the 1850s to early 2000s, the amount a single glacier has melted. Now, while this can impact people and animals today, this is another case, though, where our fossil animals give us some really good clues and some hope for how environments will respond to these changing conditions. We've already done this in Central Asia. We've already gone from our ice ages in the Pleistocene to this warmer climate today. So if we look at what animals had to move to new areas, what ones were really actually okay with this changing climate and changing environments, we can better estimate how to aid conservation, how to sort of preserve these ecosystems for future generations, as well as water resources in the area. So I think actually there's a really lot of hope that comes from using our past, looking at these fossil organisms as a way to kind of estimate what could happen in the future. And we can also use this to protect these animals themselves. This map on the far left-hand side is the modern current range of snow leopards everywhere in the world. The largest populations, or some of the largest estimates of populations for snow leopards, are in Kyrgyzstan. They're found throughout the entire country, and they still have a lot of really great habitat for them in Kyrgyzstan. This is also really close to our site, just over into the Chinese side, of our oldest snow leopard fossil. So using fossils, we can look at how these changing climates of the past, changing landscapes, similar to how people also change landscapes, have impacted where and when we find snow leopards in the past to estimate how to better protect this super amazing creature today. So a lot of kind of hope and possibilities with that. Now, I have a bunch of other slides, but I really wanted to be able to kind of pull up different slides for specific questions. So let me know what y'all want to hear more about. Living in Kyrgyzstan, finding fossils, why rhinos are the best.
Thanks, Whit. That was a great talk.
If we don't get corgi rhino trending after this, what was the point?
Corgi rhinos are the best.
It's so cute. I was like, oh, I need one.
Okay, you already have a corgi.
So they're that kind of funny nose bone on the skull. that's where their upper lip attaches. And horses are actually able to move that upper lip around a lot with even a much smaller sort of nose bone sticking out. So these rhinos probably had something approaching almost a taper-like trunk and could wiggle and move that lip around a ton, which I think the jury's out on. I think that makes them cuter. My partner thinks it makes them a monstrosity, but like...
What? No! Your partner is wrong. It makes them so much cuter. Oh,
Huh.
okay. Hashtag
Okay.
Corgi Rhino. It's a thing. We're going to make it a thing.
Yeah. Yeah. And as Wynn alluded to, in the future, you might see some more about these fossils at the Western Science Center one day soon when we open back up to the public. So keep an eye out for that, people. We'll be talking about that more when we get closer to that. So, questions. Let me go through the chat and see what we've got. There was a good question from William asking, and I'm going to pronounce this. I can do this. Where are indricotheres on the tree that you showed before?
Oh, that's an awesome question. First of all, I'll like sidetrack myself saying, for those that don't know, indricotheres are our largest land mammal to have ever lived. This is a rhino cousin that is literally 2 stories tall. Like, take a rhino, make it just big, real big, and give it a bit longer legs and a bit longer neck, and you've got this awesome critter.
It's the fossil that inspired me to go into paleontology, actually.
Oh, man, that's my like bucket list, to find an indricothere fossil. They are not super well placed in the family tree, though. They're thought to be their own family that's the sister group to rhinos currently. But the catch is that their fossil record doesn't go back as far as rhinos. So likely they split somewhere out of kind of the middle of the rhino tree and then go off on their own evolutionary adventure of being really, really, really big before tragically dying.
Really quick, William Gelnaw in the chat said, only if we can call Telesaurus Dachshund rhinos.
Oh my goodness. That's adorable.
We're just adding all these great new words to the world now.
I approve of this. Like, we need more rhinos in pop culture and more good names for fossil rhinos.
I'm not going to fight you on that.
No, I agree. This is from Mermaid Labs. Do you work with any paleobotanists to help understand the ecology of the times you study?
Ooh, another great question. I would like trade non-vital organs to get a paleobotanist to come with me and work in Kyrgyzstan. I have several sites where I have found plant material. And there is one single paper from the 1940s out of the Soviet Union looking at some both Cretaceous and Eocene fossil plant localities in Kyrgyzstan, and that is the sole summation of all paleobotany that has been done in Kyrgyzstan.
Wow. So another shout out to find Win a paleobotanist to go to Kyrgyzstan with her.
I also have a bunch of snails and I have some lizards, and like basically, please send me all of the people to help me.
All right. We'll just set up a whole group for you. Let's do that.
But that's really a great question, because without looking at these whole ecosystems, we're not kind of getting a cohesive look at how climate and how environment changed. And animals can move. Plants are not quite as good at that. So our plant communities in a lot of ways are really a better indicator of what these past environments were like. Part of why I would really, really like to sort of keep picking away at that and figuring out when exactly these environments really changed.
For things like that, for folks who may not quite understand the connection as well, like, you know, we say all the time in paleo and geology that the past is the key to the present. How do you really look at past climate and use that to study current climate change?
I think that's a really great question. I have just many other random photos. But so part of what I'm really looking at with these past climates is trying to find analogs to what was similar somewhere today and what kind of communities of critters I see there. So today, Kyrgyzstan is, again, all really high elevation, and it's really struggling with these receding glaciers, melting glaciers, less water, some of these mega droughts again. And so, what is that going to mean for the future? Are we going to continue drying it out? Or even in some of the models, as we have climate warming, we may actually even get wetter climates in some of this area. So, by comparing to especially some of our like Ice Age or late Miocene fossil sites, seeing what animals persist and don't mind when the climate change might give us some clues to what are going to be our most vulnerable players in the ecosystem today. So again, our deer, our horses are all hanging out in Central Asia for tens of millions of years and like seem to be just fine. Whereas some of these bigger animals or our carnivores really shift and change where they are through time. So these might be some of our modern groups that are biggest risk. Stuff like these snow leopards today.
Fascinating. Really important. Oh, these are awesome pictures.
To spam how cool Kyrgyzstan is as well.
Oh, here's a question from David. So does a major quake in that area, although horrible for humans, give us more or less opportunities for paleo research? So how does the Earth shift detract or help? Like, so in a area that's so geologically unstable, what does that mean for paleo?
It's one of the kind of small silver linings is one of the big hazards that comes about from earthquakes in this area isn't so much the initial earthquake, it's the landslides that can happen afterwards. So if you think about having a plate with a bunch of cake on it, if you have that at a bit of an angle and you shake it, chunks of your cake might fall off pretty easily. I always use food analogies. This is cool from a paleo perspective in that it's exposing all new rocks. It's exposing a lot of these outcrops in places where we can actually get them. It can be another geologic hazard in that, as I said, if the earthquakes weren't bad enough, Kyrgyzstan has a history of some of the largest recorded landslides ever. And unfortunately, in the 1800s, after one of the very large earthquakes in the area, there was an entire village that was buried instantly in a landslide.
Kind of
I'll add a cool random factoid, though, that from the sort of anthropological side, there's some hypotheses that this is part of why yurts became a popular and common sort of a place to live in this area, is in part because of earthquakes. They're circular and they have cross braces that move in an earthquake. So even in really big earthquakes, your yurt is extremely unlikely to fall down. And if it does, it's also not going to kill you if your yurt falls down.
Well, that's interesting.
Yeah.
Did you ever experience an earthquake while you were in Kyrgyzstan?
A couple little ones. The one that was kind of the most shaking, I was in Kyrgyzstan when there was a 8.0 that happened in Afghanistan. And Afghanistan is like 2 countries away. There was a bunch of Tajikistan in between Kyrgyzstan and Afghanistan. And it was still large enough that I was in my apartment with that beautiful view of the mountains, and like picture frames fell off of the walls and stuff was shaking. And I'm hitting refresh on the US Geological Survey earthquake reporting site. I assumed it was something like a 5 close by. And then when it showed up as very, very large, very far away, it was sort of like, oh no, that's bad.
Yeah, you can see the way our shoulders, Californians, our shoulders went up when we hear 8.0. We're like, oh no, that's huge.
A bit different than some of our California ones. And so instead of our strike slip, it's convergent. And the big difference is a lot of times these earthquakes can be at really great depths. That means it can be a huge earthquake, but by the time the earthquake waves reach the surface, it's not shaking quite as much.
That's sorry. Earthquakes are something, like, even though I'm Californian, sometimes when you talk about them, just really kind of freak me out, because, we growing up, they're always talking about the big one, right?
Mm-hmm.
And even with our great shakeout and everything, the idea of like an 8.0 is, I mean, it's all part of, geological,
Well,
just normal parts of the stuff, but it's still so horrifying. And to be able to prepare for that is like,
and that's part of what, again, even though I'm a paleontologist, we're trying to put all of this data back into making these hazard maps and kind of have education in the local country about what's going on. What are the processes that make all of this? Because with the great question about what does this mean for looking at these fossil sites, one of my fossil sites, I can only see where that rhino skull came from because there's a earthquake scarp. So when the earthquake happened, the ground separated vertically, and this vertical change on one earthquake fault in this last earthquake, which was in the 1980s, was 5 meters. The ground meters in one event.
dang.
Wait.
But that's horrifying, but also it's cool in a way because it shows this really cool intersection of different sciences, right? Interdisciplinary sciences working together. It's like paleontology helping, city future proofing for earthquakes. It's just such a cool way to show that like all of our sciences don't actually work in a vacuum. A lot of our data can help in other places.
It all feeds back in and connects to each other. Absolutely.
So there are a lot of questions, everyone. So I don't think we're going to get to all of them. However, I think there's one really good question to kind of close out. And if you're able to go on and get to the rest of the questions, feel free. But we are coming up on time. But I think this is a good question to close on. So all these fossils, do they come back to the U.S.? Do they stay in Kyrgyzstan? So how does that work when you're excavating in another country?
Excellent question. So in most parts of the world, there's museums locally. There's sort of permitting structure to figure out who has ownership rights to these. Unfortunately, Kyrgyzstan doesn't quite have all of that. So when I first was sort of asked to come help on this project, I was like, what do I do with the fossils? I need to collect them to study them, but they need to go somewhere where other researchers and public can see them and access them. And my Kyrgyz collaborator was like, oh, just take them home with you. It's like, huh? No, wait. These belong to your country. So we sort of went back and forth, and I have a signed letter from the prime minister saying that I can take fossils back to the United States. And we're working on slowly trying to get a natural history collection and a museum with a university in Kyrgyzstan. So currently the fossils I collect are here in the US, but they all still belong to Kyrgyzstan, and we're trying to have a cool collaboration between countries to sort of give them the kind of tools and infrastructure to be able to display and educate with their own amazing fossil history.
Oh, that's fantastic.
That's awesome.
That's such a great way of doing it. There's a whole history of fossils being taken out of other countries and folks not being able to learn about their own paleontological heritage there. So I'm really, really excited to hear that this is a collaborative effort for you. And also, that's really cool that you've got a letter from the Prime Minister.
It has a big wax seal and a gold stamp and a sticker, and it's real
real official.
Do you have any are you working on any educational projects to work on when you're able to go back?
So with the Western Science Center, we've been doing these amazing 3D prints of these fossils. So this is our sort of first step, is that we're trying to work on making a traveling educational exhibit that could go around to different schools in Kyrgyzstan with these 3D prints that are a little easier to transport of all of these fossils. Because this has been kind of one of the big things that's really stood out to me is the local people are so wonderful and friendly and have no idea what's going on in their backyard. A lot of the previous history of scientific work in Kyrgyzstan has been foreigners come in, do their research, go home, present at a conference, and none of the local people ever hear about what's literally in their backyard.
It's unfortunate. It's, in my experience doing educational work on Mongolia, it's the exact same story. There are a lot of, nomad communities and towns out in the Gobi, where just right next to where some of these amazing fossils have been discovered, and they have no idea of the amazing fossil knowledge that was found literally like right behind their homes. And so now there's the great work by Dr. Bolor Minjin, the Institute for the Study of Mongolian Dinosaurs, doing the exact same thing, helping others to learn about the fossils in their backyard, basically.
My Russian and Kyrgyz language skills are admittedly terrible, but I have kind of a funny language skill in that when somebody rides up on a horse to where I'm working now, I can be like, I am American, geologist, old rhinoceros bones. And then we usually get like rhinoceros in Kyrgyzstan, and I'm like, yes, rhinoceros.
Would you say it for us?
Nozorog is rhinoceros in Russian.
That's so good.
Kerik in Kyrgyz.
That's awesome. All right, well, that was our last question. Well, thank you so much, Wynn, for joining us today. And that was such an awesome talk, again, showing the intersectional, interdisciplinary work that you're doing. And thank you so much for joining us today. If people want to learn more about you or your work, where's the best place for them to go?
One easy way to get a hold of me is I'm Paleo Win on Twitter. And I love tweeting about fossils in Kyrgyzstan, and hit me up and ask questions. I mean, it takes like the drop of a pen to get me to talk about my favorite.
Yeah, so, if you had questions in the chat that we weren't able to get to today, go ahead and tweet at PaleoWin, and maybe you can get your questions answers there. So that does it for our show today. Thank you so much to everybody for joining us. If you like this program and want to support programs like it at both the Western Science Center and the Alf Museum, please check out the links in the description below on how to do that. And as always, please make sure you like and subscribe to our channel for more stories from the world of paleontology. Thanks so much, and we'll see you all next week.
Thank you, everyone.